Thank you very much for having me. This is it's been a fun conference so far. The work I'm going to be telling you about is joint work with Barkley, who spoke yesterday, and with Thomas Lamb. So first, I need to tell you what Kazhdan Lusztig polynomials are and what this combinatorial invariance conjecture is. So I'm going to be working today in the context of general Coxeter groups, so not necessarily finite. This level of generality also appeared in Grant's talk yesterday. So as a reminder, a Coxeter group is just a group W with a distinguished generating set S. The generators are all convolutions, so they square to the identity. And then the other relations are for each pair of generators, Si, Sj, to some power is the identity. And those are the only relations. This Mij here is allowed to be infinity, which just says that there's no relation between Si and Sj. So familiar examples, all dihedral groups, including an infinite dihedral group, which Grant showed a picture of, the symmetric group. So if you take the simple generators to be the adjacent transpositions, if you haven't seen this before, this is a good exercise to check that this gives a presentation of the symmetric group. The Weil group, more generally, of any semi-simple Lie group, so types A, B, C, D, and so on, or also the Weil group of any Kac-Moody group, which will give some infinite Coxeter group, or the automorphism group of any regular polytope, for example. So all of these are good Coxeter groups. Now, the Kazhdan Lusztig polynomials, they are polynomials in a single variable Q, and they're indexed by a pair of elements U and V of a Coxeter group. So I've written here that they have non-negative integer coefficients. That is true, but that is a very difficult theorem. And in particular, it won't be true from the definition I give you in a couple of slides. But these were introduced by Kazhdan and Lusztig in a very important paper, which Melissa already referred to, because it's the same paper in which they introduced Richardson varieties. So that was in '79. And they were one of the starting places where people realized that algebraic geometry of, for example, Schubert varieties is closely related to representations of the algebras. And there's a third prong here, which is representations of Heck algebra. So this one family of polynomials encodes important information about all three of these contexts. So in order to define what they are, I'll set up a little notation. So reduced word is just a word for an element of our Coxeter group in our distinguished generating set. The shortest of minimum possible length. That minimum length is called the length of W. I'll write capital T for the set of reflections in W. So these are the conjugates of the simple generators. And once we know the reflection, there's an important directed graph called the Bruhat graph, whose vertices are the elements of W. And where we have directed edges, if two elements differ by multiplying by some reflection, and we direct it from the shorter to the longer element. So this defines the Bruhat graph. This is the Bruhat graph for S3. Questions so far? So Bruhat order is just the partial order induced by this directed graph. So if there is a directed path from U to V in the Bruhat graph, then U is less than V in Bruhat order. This closed set ends up being graded by length. It's always got the identity element at the bottom. If W happens to be finite, there will always be a unique maximal element, which in the case of the symmetric group is the reversed permutation. But when W is infinite, there won't be a maximal element. And we've already seen this picture a few times. On the left is Bruhat order for S3. Notice we had sort of an edge in the Bruhat graph from the bottom to the top, which ended up not being a cover relation in Bruhat order because there was a longer path to get there. On the right, you see Bruhat order for S4, and already things are a bit messy. Bruhat order is quite an intricate coset in general. So I'm going to give a definition of Kazhdan-Lusztig polynomials. Is not necessarily going to be terribly enlightening, but I will try to point out some features that will be important. So this is a recursive definition. A priori, it's going to define some polynomials with integer coefficients, but it will not at all be obvious from what I'm telling you that, in fact, the coefficients will be natural. So as sort of the base cases, the polynomial is 0 unless u is less than v in Bruhat order. So really, we're going to restrict our attention to comparable pairs, u and v in Bruhat order. And the overall goal of what we're trying to do is to understand these polynomials in terms of that interval in Bruhat order between u and v. If u is equal to v, the polynomial is just 1. There's this degree bound that the degree of the polynomial is strictly less than half of the length difference between u and v. And then really all of the work is done by case 4 here. So this allows me to express PUV in terms of smaller Kazhdan-Lusztig polynomials Pxv. So x is in the interval between u and v. So these are things which inductively we have already computed. And then there are these R polynomials showing up, which are some other set of polynomials also introduced by Kazhdan and Lusztig, which I'll define next. So just a couple things to observe. One is these R polynomials will have signs, and there's a sign here. So it's not at all clear that this recipe is going to produce non-negative coefficients, but it does. Secondly, you might worry, okay, why does this determine PUV? Because maybe this polynomial and this shifted version of it are canceling each other in some way. Well, that actually doesn't happen because of this degree bound 3, which says that the support of these two pieces is disjoint. And so if I can compute the right-hand side, I can compute PUV. Okay. Any questions so far? Yeah. Oh, yeah, sorry, I must have mixed my notation. Wherever I wrote L, U, comma V, it's the same thing as L of V minus L of V. So these R polynomials which showed up in the last case are also recursively defined. These are easier to compute directly by implementing the recurrence. So your computer can do this quite quickly. These will have genuinely positive and negative integer coefficients. They have the same base cases, so they're also 0 unless u is less than v in Bruhat order. And then there's a recurrence based on a descent of u or v. So an element of our simple generating set S is called the descent of v if length of SV is less than length. So if we are talking about permutations and we're using the simple reflections as our generators, then this is our usual notion of descent of a permutation, except this is a left descent, so this might be inverse to your usual conventions. You could equivalently write all of the S's on the right side here, and that would define exactly the same thing. I forget why I have chosen left here, but we'll stick with what the slides say. So if I have an element which is a descent of both u and v, then I just get to translate both u and v down. So this is going to decrease the length of both u and v by 1. And the R polynomials are equal. If S is a descent of v but not of u, then I get this slightly more complicated recurrence. But in all cases, I'm either in all cases I'm lowering the length of v of the second argument, and so this will eventually produce for me some polynomial. It's not clear a priori that this recurrence is well defined, and the order in which you choose descents of V doesn't matter, but that's also true. Okay, so we've already seen both Schubert and Richardson varieties, which is well thought out on the part of the organizers. So let me just quickly summarize. So if W is the Weil group of a semisimple lead group G, and B is its Borel subgroup. So in type A that we've seen a couple times, this Borel is upper triangular matrices, invertible matrices. The Schubert variety was this closure of a B orbit in G mod B. Some people might argue that this is an opposite Schubert variety, but in Kazhdan Lusztig theory, this is the Schubert variety. And the open Richardson variety is this intersection of a Schubert variety and an opposite Schubert variety. So Kazhdan and Lusztig tell us that both the R polynomials and the P polynomials are related in different ways to the geometry of the open Richardsons and the Schubert varieties, respectively. So the R polynomial is the finite field point counts of the open Richardsons, and the P polynomial are graded dimensions of local intersection cohomology of the of the Schubert, sorry. So you should think of PUV as measuring how singular the Schubert variety XV is at the T fixed point indexed by U. So to make that completely explicit, in the finite simply laced case, so types ADE, Carroll and Peterson showed that the Schubert variety XV is smooth at the point U, if and only if this polynomial is just one. So you should think the more complicated the P polynomial is, the more singular that the Schubert variety is at that point. Okay. Now, what is this combinatorial invariance conjecture from my title? This was advertised by Lusztig. The date I've seen it attributed is around 83, and this was written down explicitly as a question in Dyer's thesis in 87, which is that suppose I have a pair of elements in W and a pair of elements in some possibly different Coxeter group W prime. If I look at the Bruhat intervals between those pairs of elements, and if they are isomorphic just as post sets, so just as abstract partially ordered sets, forgetting the elements indexing, forgetting which elements I have, forgetting even which groups I'm in. If these post sets are isomorphic, then the P polynomials should be E. So first, a couple words about why this might be surprising. Well, for one, for the various interpretations we have, the geometric interpretations, the representation theoretic interpretations, it's not clear why this would be. We have Schubert varieties of different dimensions and possibly different flag varieties. Or we have Verma modules of different Lie algebras. Not so clear why these should be invariant. It's also not clear from the definitions I gave you for a couple of reasons. So one reason why we can't just try to naively apply this recurrence here is that this recurrence specifically cared about S being a descent, that is a simple generator. But if you remember when we defined Bruhat order, I'm using what's sometimes called the strong Bruhat order, not the weak order that Gaetz was using. So for us, we had edges corresponding to any reflection. But in fact, if I give you a Bruhat interval, it's not possible to identify just based on the post set which edges correspond to simple reflections. So I can't even start to try to apply this recurrence. The other issue is that this case 3 here leaves the interval I started in. So if I start in some interval u to v, well, in this case here, I'm translating to some interval which is in the same Coxeter group, but doesn't seem to be contained, well, isn't contained in the interval I started with. So it's not clear why the information I need should be contained in my interval. Nevertheless, there has been some progress on the conjecture, so it follows from Dyer's work on R tilde polynomials, which I'll mention a little bit later, that this is true when the length difference between u and v is at most 4. Perhaps the biggest class of intervals for which it is known to be true for arbitrary Coxeter groups is the case when both u and u prime are the identity elements of their respective Coxeter groups. So this is the case of lower intervals. It was proven in a series of papers by Brenti, Duclos, Delanoy, and Brenti, Caselli, Marietti. Slightly, some of them proved the same results around the same time. Some were generalizing the prior results. There has been a lot of work in the case of the symmetric group, but even in the case of the symmetric group, the conjecture is still quite open. So there are more partial results in symmetric groups and finite groups, but still very.
Yeah. Is there anything known or conjectured if one interval is isomorphic to the opposite of the other interval?
If one interval is isomorphic to the opposite of the other, so p polynomials do not behave very well with respect to doing that. For example, like any in a finite group, any upper interval is smooth. And so if v is w naught, then all of those p polynomials are going to be 1, but their dual intervals are going to be any possible p polynomial which can show up. And actually, any polynomial shows up as a Kazhdan polynomial if it has non-negative integer coefficients. On the level of R polynomials, you might they should be equal because they have symmetry. So I'm about to say in a slide that the conjecture for the p polynomials and the R polynomials and the R tildes will all end up being equivalent, but some of them behave better than others with respect to this duality. Other questions? Okay. Right, so here are the R tilde polynomials I referred to, which are just a variable transformation of the R polynomials. So there's a unique family of polynomials satisfying this relation with respect to the R polynomials. And the nice thing about these R tildes is that they, unlike the R polynomials, have non-negative coefficients. And it's not so hard to see that we can equivalently state the combinatorial invariance conjecture for any of these 3 families of polynomials. So if I give you all of the R tilde polynomials, you can give the R polynomials and vice versa. If I gave you, say, all of the R polynomials, you could run through the recurrence here, and you can implement this only knowing the poset structure if I had given you all of the R polynomials, and so you could get the P polynomials, and so on. So just examples. Whenever we have a cover relation, the P polynomial is always going to be 1. But singularities of Schubert varieties always occur in codimension at least 4, so the hell is this? If I ever have, say, an interval looking like a 3 cube, which were some of the intervals that showed up in Melissa's talk, P polynomial is also 1. More generally, any sized hypercube will have a polynomial equal to 1. And the first non-trivial P polynomial we get is for this 4 crown. So this has polynomial 1 plus q. So you will find if you go through the quite laborious process of computing these things, say in small symmetric groups, you will almost always get 1, and only rarely do you get something non-trivial, and yet it's the case that any polynomial with non-negative integer coefficients does eventually show up as a Lusztig polynomial of some pair of permutations. So because of that, it would be nice to know something like combinatorial invariance, because computing these is not so easy. So here is our main theorem. In finite types ADE, this theorem is due to posse mode, and we prove it for arbitrary Coxeter groups. So let's have two pairs of elements from two Coxeter groups. Suppose the Bruhat intervals are isomorphic as posets. There's really one statement going on here. So these three assertions are very closely related to each other. So we get that the linear coefficients, the coefficients of Q and the P polynomials agree. The coefficients of Q and of Q to the length LUV minus 1, that is the second highest power, in the R polynomials agree, and the coefficients of Q to the L minus 2 in the R tilde polynomials agree. So there's really kind of one dimension of interesting result here, and then these three different families are related to each other by some manifestly combinatorial formula. So just to summarize now the case, the coefficients for which combinatorial invariance is known. All of these polynomials have constant term 1, or no, sorry. The P's and the R's have constant term 1, and the R tilde has 1 or 0, except in trivial cases. So those are combinatorially invariant, but not very interesting. The R's and R tildes are monic of degree equal to the length difference. So those coefficients agree. And then it follows from work of Dyer's that the R tilde polynomial, we can read off the coefficient of Q and of Q squared in that polynomial. And then you see in these 4 entries the coefficients that we had. Okay, are there questions about the statement?
Is there a difference between the question marks and dashes?
Oh yeah, sorry. So question marks are unknown. Dashes are coefficients which always vanish. So the R tilde polynomial, all of its coefficients, all of the exponents have the same parity. So this will always be 0. And the P polynomial really stops in the middle because its degree was like half the length difference. So these tops will already. Yeah.
This table is for all types.
This is for arbitrary Coxeter groups. If we included, say, if I were to draw this table just for, say, the symmetric group, then it's possible to get some more low coefficients on the R tildes, because it's possible to sort of exhaustively classify what collections of some fixed length paths in the Bruhat graph can possibly look like, and you do some finite checking, and so Marietti and Esposito have in type A pushed this further on the small powers of Q and the R tilde.
When you say this is true in type A, do you mean like both intervals have type A, or?
Oh,
one?
yeah. So if both intervals have type A, then of course not. All right. And it turns out that you can use these new coefficients we have to also show that combinatorial invariance holds for all intervals of length at most 6. So for an interval of length 6, the P polynomial can have a Q squared term, but it turns out that if you know all of the R tildes, say, of the subintervals, then you can still determine the polynomial. Okay, so the technique is going to be by something called diamond generating sets of Bruhat intervals, which was what Patimo used in finite type ADE. So this is his definition. So I'm now going to restrict to looking only at cover relations of in my Bruhat interval, not necessarily the longer edges of the graph. So I'll write EUV for the set of those. And we're going to think about collections of cover relations in my interval. And such a collection is called diamond closed if whenever I have two adjacent edges from some diamond, then I also have the other two. What do I mean by that? All of our length 2 intervals in Bruhat order look like diamonds. So if I have, say, these two edges, then in my set X, then I also must have the other two. Or say if I have these bottom two, then I also have the top two. The word adjacent in there is prohibiting this case, that if I have two opposite edges of the diamond, I'm not required to have the other two. So this defines a notion of diamond closure, which is the smallest diamond closed set containing a given set of edges. And Patimo defined GUV to be the smallest size of a set whose diamond closure is all cover relations in the interval. So it's not clear yet that this is an important notion, but it is clear that this GUV depends only on the post set. I draw for you a post set. You can check a bunch of sets. It's some finite problem. And you only need to look inside the given picture. So GUV, whatever it is a combinatorial invariant of varieties. Okay, so now I'm going to give a name to the coefficients we're interested in. So DUV is going to be this second highest coefficient of RUV. That coefficient will be negative, but I'm going to take its absolute value. And then the other coefficients we cared about are easily related to DUV. So the coefficient of Q in PUV is the number of coatoms of this interval minus DUV. Coatoms are just the elements immediately below V. The number of coatoms is a combinatorial invariant that only depends on the post set. So if we're able to show that DUV is combinatorial invariant, we also get this coefficient. Similarly, this length difference is combinatorial invariant, so we'll also get the R tilde coefficient. And the theorem, which extends Patimo's ADE result, is that for any pair of elements in any Coxeter group, in fact, DUV equals GUV, so DUV is combinatorial invariant.
How do you adopt the coefficient of Q of the R polynomial?
Oh, so that's equal up to sign to the coefficient of Q to the L minus 1. I should have said our polynomials have a up to sign have symmetric coefficients.
So that's why I think R tilde is well defined.
Yes. Other questions about that? So the proof idea, which I'll give a little more about later. So Dyer, it follows from work of Dyer that DUV, this coefficient we care about, is at most GUV. So what Dyer did is Dyer constructed some vector space, kind of formal vector space spanned by cover relations, modulo certain relations coming from diamonds. And he showed that DUV was the dimension of that space. If I have a collection of edges which is diamond generating, then it spans Dyer's space. So we get this inequality. To show the reverse, we construct an explicit diamond generating set of this size DUV. The definition of this diamond generating set is motivated by the recently discovered cluster structure on the open Richardson. Although that cluster structure only makes sense in finite or perhaps crystallographic type where there is a Richardson variety, but just modeling what what the frozen variables would be in an arbitrary Coxeter group leads us to this definition, which we can show directly is diamond generated. So we don't use results about the cluster structure, but it leads us to the correct construction. Okay, so just an example of how this works. So if I have this 4-crown interval, it turns out that any 3 of the bottom edges will diamond generate the full thing. So for example, if 3 in red do, if I bore you in the rest of the talk, you can fill in the rest of the picture and show that the diamond generate. There are many other good diamond generating sets. I could have taken a maximal chain in this interval that would have also diamond generated. So GUV is 3 for this interval. I told you before that PUV was 1 plus Q. We get that by taking the number of coatoms, which is 4, minus GUV. So that gives us that 1 there. The R tilde polynomial, the coefficient of the second highest power will be the length difference, which is 3 minus GUV. So that's 0 coefficient of Q. And these two symmetric coefficients of RUV are just equal to DUV. Okay. I also, so it turns out this number DUV is going to have a lot of different interpretations, which we will learn are all combinatorially invariant. So one is related to something called the Gabber-Joseph conjecture, which conjecturally related R polynomials to representation theoretic interpretation. So I think I already stated this. We have these open Richardson varieties. Let me restrict for now to finite type. The point counts are these R polynomials. So here's the representation theoretic interpretation. So let me take my associated complex semi-simple Lie algebra. We can index principal block Verma modules by elements of the Weil group. So for every element of our Weil group, we have some representation here of our Lie algebra. It's an infinite dimensional representation. Gabber and Joseph defined this R prime polynomial, which is an alternating sum of the dimensions of the extensions between the X groups between two Verma modules. So what is normally called the Gabber-Joseph conjecture is that R prime equals R. They did not actually state this as a conjecture. They wrote a lot of suggestive things. They said there are these things called R polynomials satisfying certain recurrences. I'm going to define something called R prime and show that they satisfy most of the same recurrences, but they did not actually state a conjecture. Nevertheless, people took it as a conjecture and worked on it. So already, predating the conjecture, it follows from Verma that the constant terms of these two are 0. Or sorry, agreed. They are 1 if U is less than V and 0 otherwise. So that is about X0, that's about Homs. And it was already known that there exist Homs between these Verma modules only when U is less than V in Bruhat order. Carlin later showed that the leading coefficients agreed and were just 1. But a counterexample to the full conjecture was found by Bo in 92. It's actually pretty hard to search for a counterexample for this because it's not easy to compute the dimension of these X groups. The R polynomials, your computer can compute just fine, but what Bo actually did was found an example of an R polynomial which was not alternating, whose coefficients were not alternating, and so it couldn't have equaled R prime.
What's the relation of the Gabber-Joseph conjecture and the Zergel-Williamson result?
I'm not sure exactly what. So, are you referring to a result that these X groups are Betty numbers of the open Richardson?
Yeah.
Yeah. So, in general, it is true. Yeah. So the correct thing
Oh, but that's about baby numbers as opposed to about.
as opposed to
point
coefficients
counts.
in a point count. Yeah. Okay, so in general, the conjecture is wrong, but we show, I think for the last remaining coefficient, which might have worked, that it is actually true. So for u less than v in W, the dimension of this X group, which was the second highest coefficient in the R prime, is equal to duv, which was defined to be the second highest coefficient in the R polynomial. And so consequently, we get this instance of the Gabber-Joseph conjecture, but also because we have shown that duv is a combinatorial invariant, we also learned that the dimension of this X group is combinatorially invariant. And so since we know in general that R prime is not equal to R, it may still be that R prime is combinatorially invariant. That would follow from some stronger things we suspect may be true, but okay. Right. So why is that? So related to Alan's question, so in order for this to happen, certain mixed Hodge spaces of Richardson's need to vanish, which account for the fact that coefficients in the point count are really some alternating sum of dimensions of mixed Hodge spaces, whereas the X groups are just a Betty number, so it's some sum of dimensions of these spaces. But because these particular ones vanish, those coefficients agree. But H322 does not in general vanish, and so the next coefficient you wouldn't expect. Okay, so lastly, I'll say a bit about how the proof goes and how it's connected to the cluster structure. Right, so the reflections, which are the elements of W that I've been talking about, are in bijection with positive roots, which is how Grant set things up. So the reflection, so W has a distinguished representation in which the reflections actually act by a reflection in that representation, and the elements that the hyperplanes that are reflecting across have normals, which are these roots. So I'll write alpha t for the root corresponding to a reflection t. Dyer defined a reflection order, which is a total order on the set of reflections or the set of positive roots, so that for any triple of roots where gamma is in the positive cone spanned by alpha and beta, gamma must occur between alpha and beta in my total order. So that needs to be satisfied for every triple alpha, beta, gamma. In finite type, if you're familiar with reduced words of the longest element, these things are in bijection with those. But in infinite type, you have no longest element, and so these are really the correct object to think about. Dyer proved that if we fix any reflection order, then the coefficient of q to the k in the R tilde polynomials is the number of increasing paths in the Bruhat graph from u to v, which have length k. Length meaning number of steps taken by the path, and increasing meaning that not only does it follow the directions of our directed Bruhat graph, but each time we use an edge, that edge is labeled by some reflection. We want the reflections we see as we traverse our path to be increasing with respect to our fixed reflection order. So it's not at all clear that this number is independent of the reflection order, but that is true. And or we have this interpretation. So this is why our coefficients are, so they have the same parity. That's right. The coefficients of R tilde, the powers appearing in R tilde have the same parity, because edges in my Bruhat graph all have odd, they connect elements whose length differs by an odd number. So the parity of the lengths of paths possible between a fixed u and v are all the same. So let's do our favorite example of S3. Remember, this was our Bruhat graph. We now include this longer edge. Let's fix this reflection order. There are two reflection orders in this case, this one and its reverse. There's one increasing path of length 3. It will always be the case that R tilde is monic, so there's always exactly one increasing maximal chain from U to V. That's here where we just read off all those in order. And then there's one other path which is trivially increasing. So the path of length 1, my sequence of 1 reflections is increasing with respect to my chosen order. So Dyer tells us that this R tilde polynomial is Q cubed corresponding to the red path and Q corresponding to the green path. So if you remember for R tilde, we're expecting to learn about the second highest power here, and we expect its coefficient to be the length difference, which in this case is 3 minus GUV. So we're expecting GUV in this case to be 2. Okay, it's not so hard to write down a diamond generating set of size 2, but how do we do it in a way that generalizes to arbitrary intervals? We have the following recipe, which has takes a few minutes to parse. So we fix a reflection order, not just any reflection order, but fix one such that the inversions of V that are the positive roots, which when acted upon by V are sent to negative roots, those must occur as the first roots in the reflection. We don't care which order they occur in, but they must all occur before any other roots occur. Such reflection orders exist, but choose any one. And let gamma 0 be the unique increasing maximal chain from U to V with respect to that reflection. Right? Told you the R tilde is harmonic, there's always this unique chain once we have fixed our reflection order. Now consider the increasing paths of second longest possible length. So the second longest possible length is length L minus 2. Consider those increasing paths. It is a feature of these particular reflection orders that once we have fixed one of these particular reflection orders, we have at most one of these second longest paths diverging from our longest path at each point, at each step of the longest path. Now, we take the collection of edges of our longest path at which no such second longest path diverges. Unfortunate negation there. The claim is that the size of the set we have just constructed is DUV, and moreover, this set of DUV many edges we have described is diamond chain. So in our favorite example of S3, gamma 0 is the red path. The first element of gamma 0 does have the second longest path diverging, so we do not include the first step of gamma 0 in our set. But the second two steps have no such diverging path, so they become these blue edges, and we can check that the blue edges do diamond generate all edges. So for example, if I start with these two, I can flip, I get the other two edges in this diamond here. I have this diamond here that I can flip down since I have the top two. And then I have many ways, say this diamond here.
Can you say again why you included the two blue edges but not the third one?
Yeah, so at this vertex on gamma 0, I do have a second longest increasing path which diverges from the red path at this point. Namely, the green path does that. So no divergence would be in my set. On the other hand, at this point, there is no second longest increasing path which diverges from the red path at this point. So I get to include this. Okay.
And the first thing in the finite type was that you had a reduced word for W off, it started with a reduced word for V.
That's right. Yep. Right. So F, the letter F here is chosen because these end up being the frozen variables in some sense of the cluster structure. So before I mention the cluster structure, I should say a word about Patimo. So Patimo had defined GUV and defined the diamond closure and proved GUV equals GUV in AVE. He did this using something called the generalized lifting property, which allowed him to apply a version of the R polynomial recurrence, which never left his starting interval. And he could track the size of the diamond generating set through that recurrence. That recurrence is known to work exactly in finite types AD. So Patimo's method doesn't extend outside of that, but the sort of broader idea of showing that GUV equals GUV does extend to arbitrary Coxeter.
So is this like the same set Patimo would have used?
Patimo, no, I don't think so. Patimo has if you trace through Patimo to get a specific diamond generating set, I think Patimo would have a lot of choices in general, so maybe some collection of choices would produce this one, but I'm not sure. Okay, so as I was mentioning, so in the case of finite file groups, we have this Richardson variety. Its coordinate ring is known to be a cluster algebra by these two groups of authors. Each extended cluster of that cluster structure has size equal to the dimension, which, as we have seen, is the length difference. So, and that extended cluster is composed of frozen and mutable variables. So the number of frozens plus mutables is the length. We showed directly that there's a natural bijection you can give between increasing paths and distinguished subexpressions. The distinguished subexpressions are used in the Deodar geometry of Richardson's. They index the cluster variables they tell you how to index the cluster variables of this cluster structure. The set of edges we use maps exactly to the frozen variables under that correspondence. So there are DUV frozen and length minus DUV many mutable variables in the cluster structure. And hence these quantities are also combinatorially invariant, this number of frozen and mutable variables. I should also mention, because showed up in Melissa's talk, so this DUV, because it is the number of frozen variables, is the dimension of this cluster torus, cluster torus. Sorry?
Of the frozen torus.
Sorry, of the frozen torus, which was referred to as the Melissa's talk. So
Christian, no other any questions?
Just make sure I understand the time. Is that maximal chain also considered diamond?
So if I take this maximal chain, this red one, that would diamond generate, but it would not be a diamond generating set of minimal size. So this GUV was defined to be the fewest number of edges we need to diamond generate the full.
Question is the red one plus a green one also considered diamonds?
Oh, I see. So the question was, is this kind of half hexagon here considered a diamond? So the way I define diamond generating, we only include the cover relations. So we don't need to consider this. However, there's another presentation of, well, it turns out that if you include the long edges among your generators of a Dyer style vector space, and then you also include relations like this one, that you get the same dimension. So you could have done everything where you have a generator for the long edges, and in that case, there would be a relation corresponding to this, and so it would be the case that if you had two of these, then you should get the other two.
Reason that you want to take a touch more such that the immersion creates.
Yeah, so it doesn't work if you don't do that. So there can be more than one diverging path at a given point. That if you don't have that condition, you should think of it as being like on the cluster side, people start with reduced words for V, and that's some of the same choice.
Is the combinatorial invariance of the number of frozen variables known before this?
No, so it's no, it wasn't known. So it's probably experts knew before this that that coefficient of the R polynomial should be equal to the number of frozens. It's not literally in Lamspire because the cluster structure on the Richardson is not locally acyclic, but a different technical hypothesis does the same work. So experts knew before this that DUV was equal to the number of frozens, but not that DUV was combinatorial invariant.
You mentioned that one of the problems is like not knowing which edges are given by left descents. If you were to take like decorate your diagram and to know exactly which ones are given by left descents, take isomorphism for that object. Is invariance known for?
So the trouble is you're going to get a lot of intervals which have like no descents at all in them, and so I don't, certainly if your interval happens to have a lot of descents in it, and if you are told, which upper edge corresponds to the same simple reflection as which lower edge, you can start to implement the recurrence, but there's going to be a lot of intervals in which you can't even start because there's no descents that confine themselves to that interval, so that's not completely clear. Okay.
So can you like reverse engineer, like if you have a Bruhat interval, can you define a cluster structure?
So that is an interesting question because, for example, this gives some notion of frozen and mutable steps on a maximal chain in a Bruhat interval in an arbitrary Coxeter group in which there is no Richardson variety. You could wonder, well, can I write down some quiver from that data to get a cluster algebra? Probably you would get like some gross algebraic numbers in your matrix. So I don't know. I mean, probably to somebody that's a cluster algebra, but I don't know what. Yeah, so it's an interesting question whether one can get some interesting range out of doing that.
Okay. Another question. So the fact that there's a unique increasing path that's somehow related to the order complex being contractible, like is there a topological interpretation of DUV in terms of the order complex?
I don't know an interpretation in terms of the order complex. So one connection is that you can prove that for any interval, if I take any maximal chain of it, that thing will diamond generate the full interval. And that's because the maximal chains are connected to each other under diamond flips, which is related to the topology of the order complex, but I don't think I know anything else to say. Thanks.
Let us thank Christian again.